Hello everyone and welcome to this machine learning playlist. Today we are covering an important topic, so whether you're someone who is absolute beginner or you have some experience with machine learning, this playlist has been designed in such a way that it will be easy to follow for everyone. Also packed with lots of values and information, and it will be really helpful for you, especially if you're preparing for a machine learning based job role like data analyst or data scientist. So please subscribe to the channel and drop a like below to support our work. And without any further delay, let's get started with today's topic.
So with this lecture, we are going to cover the first boosting algorithm within our machine learning playlist. And today we are covering AdaBoost. Followed by this lecture, we are also going to cover gradient boost for regression and classification both. And then extreme gradient boosting for again regression and classification, both types of problem statement. For the time being, let's keep our focus only on AdaBoost. As a prerequisite for you, I'm expecting that you are already familiar with the topics like decision trees, random forest, and you have some high-level overview understanding around tagging and boosting algorithm as a whole. In case you need more clarity for any of these topics, then feel free to check it out from this particular machine learning playlist. I will provide you the link below in the description box. However, if you are already down with all these topics, then without any further delay, let's move ahead. So we are going to understand the AdaBoost algorithm by taking a step-by-step approach. And at a time, we will be talking about one particular step. Also, we have this particular data set that we are going to use as a reference in order to understand AdaBoost. This data set has 4 features and one target variable, which is ceiling. So depending upon these 4 features, which are outlook, wind, temperature, and storage, we need to predict whether ceiling should happen or not. So you can see the values for ceiling is either yes or no. So the first step for the AdaBoost algorithm training is assigning weights. Let's understand what that is. Assigning weights means we are creating a new column over here called weights, and the idea is to assign a value for each and every record that should be absolutely equal. So we are going to assign the same value for each and every record within this data set. And one of the easier way to do that would be, since we have 16 records within this data set, then each and every record will be assigned a value of 1 by 16 like this, from top to bottom over here. Now, naturally, you will have this question in your mind that how exactly this new feature is helping us to create an efficient machine learning algorithm. Of course, we will understand each and everything in absolute details by the end of this lecture. So just stick to it. The second step talks around creating stumps or weak learners. Let's understand first that what is a stump, then we will understand that how do we actually create it. In the previous lecture of random forest algorithm, which is a bagging technique by the way, we have seen that each and every model will be a fully grown decision tree. And decision trees have a property of low bias and high variance. And this is why within random forest, we train multiple decision trees like this in order to create a final model that will be a low bias and low variance in nature. In contrast, when we are talking about a boosting algorithm, then instead using a fully grown decision tree that will have a nature of low bias and high variance, we will use a tree of depth 1. In simplified terms, this tree will have one root node and 2 leaf nodes like this, and this depth will be 1. And this thing actually is called nothing but stump. So what I'm trying to say is, when we are talking about AdaBoost technique, which is a boosting algorithm, then these models will not be a fully grown decision trees. In fact, these will be a decision tree with a depth of 1, which is called a stump. Now, obviously, you can understand that a stump or a decision tree with a depth of 1 will not be that good in terms of performance. And you have guessed it right. Actually, a stump is called a weak learner because it has the nature of high bias and low variance, which means its performance will not be good enough in terms of the training data. However, it will be somehow better in terms of the testing data. And the idea is to combine multiple weak learners like this in order to create a final model that will have the nature of low bias and low variance. So I hope that now you have some clarity around what is a stump or a weak learner. Now these two steps, which is creating a stump and choosing the best performing stump, talks around that how do we simply come up with the base learning model. So let's try to understand how that happens. So we have discussed earlier that a stump would look something like this, and yes, that's the one. And let's say for this particular stump, we are considering this feature outlook and its value as sunny. So considering the feature outlook and its value as sunny, we need to obtain these two leaf nodes. So we have the values of sunny here, here, and all these data points. And when the outlook is equals to sunny, it has 4 yes and 3 no's. In contrast, let's talk about the records where the outlook is not sunny. So these are the records where the outlook is not sunny. And upon observing carefully, you will notice that all these data points have 5 yes values and 4 no values. So the way we have created this particular stump, few more stumps will be created like this. So let's say S2 is the second stump, S3 is the third stump, and S4 is the fourth stump. And these could be the stumps where the outlook value has been considered as rain, or maybe it has considered as overcast, or maybe a different feature has been considered. And previously within the lecture of decision trees, we have already covered the topics like entropy, Gini impurity, and information gain. So of course, these are the measurements that helps us to decide that which model is coming up with the purest leaf nodes. In case you are not familiar with all these topics, then please consider checking out the decision tree algorithm lecture within this playlist. Link is provided below. So ultimately, going by these measurements, we finally choose a weak learner model which is performing the best among the rest of the others. So we have covered that how the stumps are being created and how do we choose the best performing stump. Now the next step is to calculate the weights for each stump. Now this would be something absolutely new to you. Why do we exactly need to calculate the weights for our model? So basically what we are doing is, let's say just for example that for our AdaBoost algorithm, we are training only 4 weak learning models. Then each and every model needs to be assigned a value like this. And these are called the weights for each and every model. But why are they exactly assigning weights to them? If you remember, when we covered previously the topic of random forest algorithm, over there we did not use the concept of assigning weights to our models, because let's say this one is a random forest algorithm where we are training these 4 models, and let's say that for a given classification problem, this model is predicting the value of 0, this is predicting 1, this is predicting 0, and this one as well is predicting 0. In that case, we have learned that we will go by the majority and the final output will be classified as 0. It happened because each and every model within the random forest algorithm had equal amount of say, which means their votes were treated equally. And this is where we decided to go with the majority. However, in contrast, when we are talking about boosting algorithms, especially AdaBoost, this is not the case. So over here, let's say the weight for the first model is 0.1, second model is 0.3, third model it is 0.2, and fourth model it is 0.7. Then our output will be based on what this particular model is saying, which has the highest value of weights, or you can say the highest say among all the other models. And this is the area where it indicates that among all the weak learners, this one is the strongest in terms of doing prediction or its performance. And this is why it is important to understand this step where we are calculating the weights for each and every stump. I hope that now you have understood that why exactly we need to assign weights to our base learning models or our stumps. Now let's try to understand that what is the formula that helps us to calculate the weight for each and every base learning model. So this will be the formula to check the performance of each and every stump, or its output will be the weight assigned to one particular model. Over here at the place of E, we will assign the value of sample weights, which in our case is 1/16. If you remember, here we assigned the same weights to each and every record, which was 1/16. the same value you will be providing over these two areas in order to calculate the final weight. And as I've said earlier, that if you have 4 weak learning models like this, in that case, the model with the highest weight will have the maximum say, or will have the maximum impact in terms of predicting the final outcome. The next step is where we adjust and normalize the sample weights. So let's understand this step very clearly, because this is the most important step of this entire algorithm. So over here, we are talking particularly about adjusting and normalizing this particular weights. Okay, so let's talk first around that how are we exactly adjusting these weights. First, let me quickly erase all of this from here so that we can have a nice and clean screen. Okay, let's understand like this. Let's say that we have 4 data points like this. We have values 1 and 0. Okay, and we have assigned 1 by 4 to each and every record, which is nothing but 0.25 like this. And let's say that when the first weak learning model is doing the prediction, then it is classifying this point correctly, it is classifying this point correctly, it is misclassifying this particular point, and then it is classifying this one as well. Absolutely fine. Now what we need to do is, what we exactly want to understand, that how do we take these weights and then how exactly we are adjusting it, and then what is the way to normalize it. So we adjust these weights in such a way that all the correctly classified data points becomes a really small value like this 0.03 or let's say 0.02. However, in contrast, we will increase the weights for the incorrectly classified data points. Like for this one, let's say 0.31 for this incorrectly classified data point. Then again, for the next one, which was classified correctly, I will keep it a small value. By the way, we do not adjust these values manually. There is a particular formula that will adjust all these values, but just to provide you the clarity, I am doing it manually over here. So we understood that how these weights are getting adjusted. There is a particular formula to do this that we are yet to cover within the same lecture. But the idea of adjustment is that all the correctly classified data points will have a significantly lower value, and the incorrectly classified data point will have a higher value. Now the next thing is to normalize these weights. Let's understand first that why exactly it is needed. So over here within the initial weights column, if you sum up all these values, you will get a value of 1 as a sum. However, after adjusting the weights going by one particular formula, you will not get a sum equals to 1. And this is why it is important that we take all these values from the adjusted weights and we modify it in such a way that final sum will be equals to 1. So I hope that I was able to provide you a high level understanding around how do we take these weights and then how do we adjust it and then normalize it. Now let's move ahead and look into the formula of adjusting the weights. So this is the formula to assign new weights. The first formula is for all the incorrectly classified data points, and the second formula is for all the correctly classified data points. Now without going deep into the mathematical calculation, let me tell you straight away that these formulas works in such a way that if we provide the same weights to both the formulas, then for correctly classified records, this value will be converted to a significantly lower value, and for the incorrectly classified data points, this will be converted as a significantly higher value. Stick to the video and we will discuss that why exactly we are doing this, assigning lower weights to correctly classified data points and assigning higher weights to incorrectly classified data points. Okay. And by the way, if you're wondering that what values to put over here within this particular formula, then this weight will be the initial weight that we have. And this performance value will be the weight of this term that we saw earlier, that how to calculate using this particular formula. So if you remember, we assigned weights to each and every model, and the model with the highest weights will have the highest say in the final output. So I hope that now you have some clarity around how do we take the previous sample weight and then going by these two formulas, we adjust it to new weights. And then these new weights or these adjusted weights will be normalized. And now this final normalized weights helps us to understand that after training the model 1, which records from the entire data set will be feed forwarded to the next model, which is model 2. And we have already discussed earlier that when we are training the next model, it will focus more on the mistakes made by the previous model. So let's understand how these newly normalized weights is helping us to feed forward the incorrectly classified records. So now we are going to discuss about the final step, which is data preparing for next stage, which is data preparing for the next model for this one. So let's discuss this further. Let's suppose that this one is the normalized weights that we have, and consider that summing up all these values, you will get the final sum of 1. And with the help of these normalized weights, we are going to calculate the data set for next stage. So this first record as 0.1 will remain 0.1 over here. For second record, we will sum up these two data points and we will have 0.3. For the third record, we will sum up these three data points and we will have 0.4. And this one is an incorrectly classified data points by the previous model. This is why it has a higher value. So when we sum up all these data points till this point, we get a value of 0.74. Again, going forward, these two are correctly classified data points, so they have a lower value. So these becomes 0.78 and 0.81. Now observe carefully that these two data points have a small bin like this, starting from 0.1 to 0.3. Again, these two data points will have another small bin like this, let's say, but these two data points will have a larger bin, something like this, because it is going from 0.4 to 0.74. And we are getting this large bin just because of the incorrectly classified data point. Again, from 0.74 to 0.78, we will have another small bin like this. And from 0.78 to 0.81, another small bin like this. And let's say after the training of first base learning model, when we are forwarding the data set for the training of second base learning model. And in order to do this, if we are forwarding the records based on this newly normalized weights, then we will have the highest probability of sending those incorrectly classified data points which has this largest bin. Of course, we may also pick data points which were correctly classified by the previous model, like these ones, but mostly we will forward only those data points that were incorrectly classified by the previous model. So I hope that you are clear till this point. And with that being said, we have covered all these steps in order to train an AdaBoost model. First, we saw that how do we assign weights that will be a same value for each and every record. Then how do we create multiple stumps and then choose the best performing one with the help of entropy or Gini impurity. Then we calculate the weight for each and every stump like 0.1, 0.2, 0.4 and let's say 0.8. We adjust and normalize the previous sample weights that we assigned on this point. And finally, we prepare the data for next stage considering the newly normalized weights. We will repeat this entire step for n number of times if we have n number of base learning models within our AdaBoost algorithm. For example, if you are going to train 10 base learning models, then you will repeat this entire step 10 times for your boosting algorithm training. And then finally, when you are predicting the output, you will consider those models that will have a higher say or higher weights in order to do the prediction. Thank you very much.